Hi, everybody. I hope you had a good night. We're picking up where we left off the other day on collisions in two dimensions, taking a little bit longer look at that, some more mathematics. And I was thinking about doing an Excel worksheet. I don't think I'm going to do that, but we'll look at a couple of old AP problems as well. Take a quick look at this. Most of you have played billiards before. In billiards, the cue ball is equal to the mass of the ball you're hitting. So the initial example here is here's your cue ball moving with some initial momentum. It hits the second ball, and most of you know that if you hit it straight on, the cue ball will stop and the other ball will take off with the same velocity. But there's something very interesting. If you hit it just slightly askew off to one side, the cue ball will travel off in one direction while the ball that was hit will travel off in another direction. Now, what does that mean? Well, there's something interesting here, of course. Both momentum and kinetic energy have to be conserved because it's an elastic collision. But if momentum's conserved, since the mass of the cue ball and the mass of the cue ball and the other ball that was hit are all equal to each other, this equation becomes this, which is interesting in itself. But remember, these are vector quantities, so you just know that the initial vector, velocity vector, has to equal the sum of these two velocity vectors if you somehow drew them, although these are momentum vectors. But here's the more interesting part. If kinetic energy is conserved, the initial kinetic energy of the cue ball equals the final energy of the cue ball plus the final kinetic energy of the other ball. And if the masses are all the same, and all of them have 1/2 in front of it, you end up with this very interesting equation, which states that the square of the sums of the final velocities has to equal the square of the initial velocity. Now, wait a second here. Let me quick redraw this down here. What we have is this first statement up here simply states, all right, the sum of the final velocity of the cue ball plus the final velocity of the other ball, these two vector quantities have to add up to the initial velocity of this. But it doesn't say anything about this theta here. But if these three quantities obey this, then this has to be a right triangle. We still don't know this theta here, but we know that this angle over here has to be right. Why? Because a squared plus b squared has to equal c squared. A squared plus b squared equals c squared. So this over here has to be a right angle. What does this mean? In billiards, if you hit the cue ball against another ball, the angle these two objects make with respect to each other is always 90 degrees. And you're like, what? No way. Yeah. If you just barely hit it, I mean, just barely hit it, then the cue ball would end up going pretty much straight this way, and the other ball would go off this way. Any other angle, it ends up being 90 degrees. It's still 90 degrees. The only exception to that rule is if you hit it straight on, in which case the angle between the two is exactly 180. But yeah, it's an interesting problem. Try it next time you get a chance to play billiards. I wanted to give you an example with some numbers in it. So in this case, an air hockey puck, which has this mass, is traveling at this speed. It collides with object B, which is twice as massive. Object B goes down this direction at 37 degrees relative to the original velocity. And the original puck bounces off this way and goes off at 65 degrees relative to its original speed. The question is what are the two speeds of these two final objects? Well, we've got to do this in terms of momentum. And just momentum alone is enough to solve this. Why? We know the momenta of these two objects, A and B, after the collision, have to equal to this initial momentum, which is just 5.5 times its mass. So what can we do? We can figure out the momentum of object A. Well, it's going to be its mass times its final velocity. Is that, I'm supposed to say an A there? Whoops, sorry, it's a mistake. And the momentum of this object, which is going to be that times velocity B. I guess that is an A up there. Sorry, my vision's going bad. How do we add those two momentum vectors? We're going to have to break them into their components. Luckily, we know the angles, and so we can figure out both the vertical and horizontal components of each one of these. Now, what's interesting is this. What do we know has to be true about the sum of these two horizontal pieces? I don't know how to draw that one. That's interesting. That's supposed to be blue. The sum of these two have to equal this initial momentum vector over there. In other words, we can write it this way. Here's one of them, plus the other one has to equal the initial. Why? Momentum has to be conserved, and these are the only horizontal components afterwards. Likewise, what else do you know? These two vertical components of momentum, even though they don't look this way in my drawing, have to be exactly equal in magnitude, but opposite direction. Why? The initial momentum was only horizontal. It didn't have a vertical component. And so even though these both have vertical components, the sum of these two vertical components must add up to 0, or their magnitudes must be equal to each other. If you solve these two equations on your handy-dandy Inspire, menu 371, type in the two equations and solve, you'll discover that the two velocities of the two pucks afterwards are just these two numbers. It's not bad. Momentum conservation, two-dimensional collisions are not bad at all. I thought about doing an Excel one with you. You can actually do two-dimensional collisions very nicely in the center of mass reference frame, but the velocity of the center of mass is now moving in 2 dimensions, and it's usually better to do this in an Excel sheet. But I tried doing it beforehand, before I recorded this video. It's going to be just too painful for you to try to follow, and especially if you don't happen to have Excel on your computers, or if you don't have your computer with you. Here's another example of equal mass elastic collisions. In this case, a proton runs into another proton, and there's a magnetic field, so it bends a little bit, but this initial angle here is, or should be, 90 degrees. Oh, that's hard to see. Please realize there's a bit of perspective error here as well. This is not quite perfect. Want to wrap things up with 3 AP problems that involve conservation of momentum. In this case, if you read it, a small block of mass 2m is initially at rest on a track at the bottom of a circular loop-de-loop as shown above, which has radius r. Okay. The surface contact between the block and the loop is frictionless. Oh, good. A bullet of mass m strikes the block horizontally with initial speed v0 and remains embedded in the block as the block and bullet circle the loop. Determine each of the following in terms of m, v0, r, and g. A, the speed of the block and bullet immediately after impact. Well, momentum must be conserved, so the momentum of the bullet beforehand has to equal the momentum of the block bullet system times the final velocity. What's the final velocity? It's going to be 1/3 of whatever velocity the bullet was moving at. How fast is it moving over here at point P? Well, at point P now, so remember when the bullet embeds in here, we have heat generated. And so we can't just use energy conservation to get this velocity. You'll get the wrong answer. But momentum's always conserved. Momentum can't be converted into any other quantity. It can't be converted to heat. It's just momentum. And so the collision there, we can use momentum to solve that one. But now after the collision, we can use energy. Why? Once it's embedded in here, all the heat's already been dissipated. Sorry, I can't try. I'm trying to heat dissipated. There we go. Here's the heat coming off. But once it's embedded and it's moving with this velocity, no more heat's being generated. And now we can just take a look at the initial kinetic energy of our block bullet system, plus the potential gravitational potential energy, GP, it's going to have at this point, and figure out what the final kinetic energy is going to be. So plugging in our numbers, 1/2 mass, which is now 3m, times the initial velocity, which we know is v0 over 3 squared, equals its GP at this point. Remember, its mass is going to be 3m, because it's got the bullet embedded in it. Its height is r. So mgh plus the final kinetic energy. And if you solve for the final kinetic energy, just rearranging this equation, can't do much with it. It's just mv0 squared over 6 minus 3mgr. Here's the 3 mgr. This reduces down to mv squared, v initial squared over 6. The minimum initial speed of the bullet if the block and the bullet are to successfully execute a complete circle of the loop. Well, that means up here on top, it needs to be moving with the speed that's large enough so that the centripetal force is provided exactly by gravity as it slides across here. There's no additional force required. So in C, at the top, centripetal force must equal mg, or in this case, the centripetal force, the mass of the object times v squared over r, must equal mg. And if you calculate it real quick, its velocity needs to be the square root of gr. Now, using just the work energy or energy idea, the initial energy at the bottom is 1/2 mv squared. Remember, this is the initial velocity of the black bullet system, equals the GP it has at the top. Notice that the height is 2r because it's now 2r up above here. It's its height, plus 1/2 times mass times the velocity we need to have at the top, which is, remember, this number right here. And if you solve that, you should discover that the velocity that the bullet needs to have at the beginning, that is right here, needs to be the 3 times the square root of 5 gr. I realize it's an ugly answer, but that's what it is. Take a look at this one. Here's another mechanics free response question, level 1. A massless spring with force constant 400 is fastened at its left end to a vertical wall as shown. Initially, block C and block D rests on a horizontal surface with block C in contact with the spring, but not compressing it, and with block D in contact with the other block. Block C is then moved to the left, compressing the spring a distance of 0.5 meters, and held in place while block D remains at rest, as shown. Use G equals 10. Determine the elastic energy stored in the spring. So just again, remember, elastic potential energy is just 1/2 k delta x squared. So plugging in our numbers, we get 50 joules. Now, block C is now released and it accelerates to the right towards block D. The surface is rough and the coefficient of friction between each block and the surface is 0.4. The two blocks collide instantaneously, stick together, so we have an inelastic collision, and move to the right. Remember, the spring is not attached to block C. Determine each of the following. The speed of the block just before it collides with block D. Using the work energy theorem, we know how much energy it starts out with. That's actually not kinetic energy, but that's okay. The energy it starts out with, I really should have written this as initial energy plus work equals final energy. 50 plus the work done. Now, the force of gravity on the block is going to be 4 times 10. Remember, gravity is 10 in this case, times the coefficient of friction gives us the force of friction, times the distance it moves, times the cosine of the angle between the force and displacement. This whole term gives us the work done. And the final energy is just going to be kinetic energy of just that 4 kilogram block. So 1/2 4 times v final squared. And we get this is the final velocity of block C after it's lost some energy due to friction sliding across that rough surface. C, find the velocity of the two blocks just after they collide and stick together. Well, now we can use momentum conservation. We know the 4 kilogram block that we just solved was just moving at this speed that we just found up here. And after they stick together, the mass is going to be 6 kilograms times the final velocity. And so our final velocity should be 3.06. And then finally, D, how far horizontally will the blocks move before coming to the rest? Remember, this surface has friction. Solving it, initial kinetic energy, 1/2 total mass times the velocity we just solved, squared, plus the work, which is going to be the coefficient of friction times the normal force, times delta x, times cosine of that, and the final energy in this case is going to be 0. And if you solve this, and if I didn't make a mistake, you'll discover that they'll slide about 1.17 meters before coming to a rest. Finally, here's a mechanics level 3. Two blocks, 1 and 2, are shown, and they have masses m and 2m respectively. Block 2 has an ideal massless spring attached to one side. I love these massless things. When block 1 is placed on top, the spring is compressed a distance d at equilibrium. Express your answers to all parts of the questions in terms of the given quantities and physical constants. A, determine the spring constant of the spring. Well, that's not too bad. Just using Hooke's law. Force is equal to negative k times delta x. The force is mg. The distance it compresses, I told us, is capital D. So the spring constant is just mg over d. Now, don't worry about the negative signs here. Just remember that negative sign just defines the fact that the force and the displacement are always in opposite directions. Oops, I jumped a little far ahead already. Later, the two blocks are on a frictionless horizontal surface. Block 2 is stationary. Block 1 approaches at speed v0 as shown. B, the spring compression is the maximum when the blocks have the same velocity. Briefly explain why this is so. If the objects are and here's my explanation, if the objects are in contact and the velocity of block 1 is moving faster than this block, then the spring is still being compressed. If the objects are in contact and this object and the spring are moving faster than block A, that means the spring is extending. Therefore, maximum compression must occur when both blocks are momentarily moving at the same velocity. I don't know why that little slash is doing there. C, determine the maximum compression of the spring during the collision. How do we solve that? First of all, we have to figure out how fast they're going to be moving during the collision. So using momentum conservation, initial momentum is just m times v0. The final momentum, when they're briefly moving together, the mass is going to be 3m. Remember, the spring is massless times v final. And the final velocity is going to be v0 over 3. Briefly, when they're all both moving at the same speed. Now, using energy conservation, we know the initial kinetic energy plus the energy stored in the spring plus the final kinetic, or has to equal that plus the final kinetic energy. This has to equal that. So the initial energy of the first block is just that, equals the energy stored in the spring, which is 1/2 kx squared, and we're going to use the k we got from up here and stick that in there, times delta x, plus the final kinetic energy of the two blocks, which is 1/2 their total mass, times their final velocity squared. And if you solve that, and if I did my math right, you'll get delta x is equal to the square root of 2v0 squared over 3g. Yuck. Finally, determine the velocity of block 2 after the collision when block 1 is again separated from it. Well, this is a perfectly elastic collision. It's on a frictionless surface. And so you can either, and the velocity of the center mass must be moving at v0 over 3. That's how fast they're moving together later. So either using the simultaneous equations, conserving momentum and energy, kinetic energy, and you could solve it that way, or my way I love doing it, of course, is from the center mass reference frame. If the center mass is moving this fast, that means beforehand this object's approaching it at 2/3 of that, which means afterwards it needs to be moving away at, I may have done my math wrong down here. It needs to be moving away at 2/3. So oh wait, no, it's right. But since my velocity is moving that way there, yeah, the velocity of object 1 should be negative v0 over 3. And likewise, by similar logic, block 2 should be 2v0 over 3. Why? The center of mass, I guess I should probably draw it up here, then I wouldn't make my mistakes. The center of mass here is moving at v0 over 3. I don't have it quite in the right spot here. So beforehand, this object is getting closer to the center of mass by v0 of 3. Afterwards, it needs to be moving away at v0 over 3. But since the center of mass is still moving this fast, it needs to move at 2 v0 over 3 to satisfy that. Yeah, it's kind of ugly. Number 73 is not a very difficult problem from your homework tonight. It's only a 1-star problem. But it's one that's caused, I usually get questions like, or on it almost every year. So take a look at it. 2 long barges are moving in the same direction in still water, one with a speed of 10 kilometers per hour and the other speed with 20 kilometers per hour. Oh, crud, no, I did this wrong. That's all right, I'll fix it in a moment. While they're passing each other, coal is shoveled from the slower to the faster one at the rate of 100 kilograms per minute. How much additional force must be provided by the driving engines of the faster barge and the slower barge if neither is to change speed? Assume that the shoveling is always perfectly sideways and that the frictional forces between the barges and the water do not depend on the mass of the barge. So, we know that impulse is equal to force times time, which is equal to the change of momentum. You can rearrange that, and we've done this earlier in our last video. Force is equal to the change of momentum over time. So we can solve this fairly elegantly with this. So in this case, it's not the change of, we can rewrite this as the change of velocity times mass over time. And here's where I made my mistake. These are in kilometers per hour. So I need to convert those to meters per second when I plug it in here. So my apologies, that's wrong. But the mass per unit time, it's 1,000 kilograms per minute, so 1,000 over 60. And if you convert these into meters per second, you'll get the force on the faster barge, or the force it needs to actually push. What's B? Here's the interesting part. These guys are just throwing the coal sideways off of this barge here. It's actually not changing speed at all in this direction, left or right. So its delta V is 0, and the force this barge needs to exert is actually 0. Now, some of you are saying, but wait a second, doesn't it gain velocity this way as they throw it? Yes. It does tend to make the barge tend to want to go this way slightly. There's a force this way. But because we're not told how fast they're throwing it, we actually can't calculate this, this force down here. And I guess we're assuming that the barge is so massive that it's an insignificant force compared to, or insignificant acceleration as well. But yeah, it's an interesting question. So the incorrect part on this one are these two velocities. If you fix those, you'll have the right answer. Good luck with your homework tonight. You should have, it shouldn't be too bad. Momentum is not a bad chapter. Two-dimensional collisions are a little bit more exciting than most. Talk to you soon. Bye.